Hello, calculus students. On the topic of trigonometric, or just simply trig substitution, which is a method for approaching certain kinds of antiderivatives. I'm actually going to temporarily skip this slide and actually just show you the magic of trigonometry on doing an integral such as this one. We have the antiderivative of the square root of 16 minus x squared. Up to this point, none of the methods that we have practiced are going to be useful. For example, try a basic substitution, let u be the inside, and then the derivative of that would be negative 2x dx. But there's no x here to help construct the du. So a regular substitution doesn't work. Well, I'm going to show you something here that does work, and it's absolutely fantastic. I'm going to do a substitution. Instead of calling something in here u like that, I'm going to let x be a new expression, one that will let me use trigonometric identities to help ultimately solve this task. I'm going to let x be 4 times sine of u. So this is a substitution in the sense that we're changing x into a new expression involving a new variable. If x is equal to 4 times the sine of u, then the next thing you want to do is say, what is the derivative of x? Well, the derivative of x is 4 cosine of u. And then don't forget the du that we have here. But let's see how this is at all useful. Okay, so we have this radical. Inside the radical is the 16 minus, and then I'm replacing x with 4 sine u. And that needs to be squared still. Of course, we have all that inside a radical. And then we also need to change the dx. The dx becomes this expression right here. So times 4 cosine of u and then du. Okay, so at first glance, it looks like I really complicated the integral. But watch what happens through the power of trig identities. Okay, so this 4 sine of u, that's going to be squared. You can square the 4 and the sine u separately. So this reads 16 minus 16 sine squared of u. Now, because I chose this to be 4 in my setup here, when you square that 4, it makes a 16, which matches the other number that was present inside this radical. This needs to happen so that this number now that's common can be factored out. The 16 factors, leaving just a 1 minus sine squared of u. Now it's all still inside a radical, mind you. And then we have this rule, right? If you square root a product, the square root of a times b, you can square root them separately. Be careful you don't do that for a sum, right? If you have a square root of a sum or a difference, do not do this, right? But these are not at all the same. Some of you might have thought, looking at this problem originally, is, hey, just square, isn't that the same thing as just doing 4 minus x? Because you can square the 16 and the x squared separately. And that is a big no-no. You cannot just simplify that to 4 minus x. However, at this stage here, I can square root the 16 and square root that separately. Also notice that 1 minus sine squared, using the Pythagorean identity for trig, that's the same thing as cosine squared. In fact, that's the real reason that I did the substitution in the first place. So instead of a 1 minus sine squared right there, we have a nice clean cosine squared of u. Now I can square root the 16 and the cosine squared separately. Square root of 16 is 4, and square root of cosine squared is cosine of u. But then we still have this 4 cosine u over here. The 4 times 4 make another 16, and that can be factored out to the front. And then the cosine times cosine make cosine squared. All right, now I want to take in what just occurred. This is the magic I was just referring to a moment ago. We started with an integral that had nothing to do with trigonometry as far as we could tell, and by making this kind of substitution called a trig substitution, I was able to ultimately convert this to a trig integral. So for cosine squared, that becomes 1/2 times 1 plus cosine of double the angle of 2u. The 1/2, I'm going to just go ahead and multiply it with the 16 and make an 8. So we have to anti-differentiate the 1, which is u. Don't forget that we have to do it with respect to u. And then anti-differentiate cosine 2u. That's going to be sine 2u, but with a 1/2 in front to counter the chain rule. And then plus c. Okay, I'm going to distribute the 8 across the parentheses first. So we have 8u plus 4 times the sine of 2u. Now, in order to be able to convert this back into x's, which ultimately I want to do, because I started with an integral in x, and so I should have an answer that's dependent on x, not dependent on u. I'm going to have to make use of the double/half angle identity on sine 2u. Recall that the sine of 2u can be written as 2 sine u cosine u. So then I could write my answer now as 8u plus 8 sine u cosine u plus c. Okay, now we need to do some sort of back substitution, get back to the x's. And the key is in this statement right here. Okay, we know that x is equal to 4 times the sine of u. I can take this expression and solve it for u and see what I get. So I'm going to divide both sides by 4. X fourths is equal to the sine of u. And isolate the u, you need to do an arc sine of both sides, right? The inverse sine is how you cancel a sine. That's what inverse functions do. And so u will be the arc sine of x fourths, which you could also write this way. So that's going to help me do a back substitution right here, so I'll be able to just turn that u into an arc sine of x fourths. I could also just change those u's to arc sine of x fourths, but then you wind up with complicated looking expressions that the sine of the arc sine and the cosine of the arc sine. So I'm actually going to take this a little bit further by creating a reference triangle from this line right here. Keep in mind that we're doing the sine of u to get this ratio, which means that u should be interpreted as an angle in a right triangle. Right? So the angle measurement would be u, and the sine is the opposite over the hypotenuse. That tells me I should label the opposite as x and the hypotenuse as 4. I can use Pythagorean theorem next to get the missing side. Right? You can call this a for a moment. Okay, so we know that a squared equals hypotenuse squared. Now keep in mind I'm trying to solve for a, so I'm going to say a squared is equal to 16 minus x squared, and then take a square root. Okay, so we have a complete triangle now. Okay, now how this is useful is in any statements that involve a u that doesn't have it's not a trig function of u is just by itself, I'm going to use this to do the back substitution. But any part of my answer that has a trig function of u, and there's 2 of them here and here, I'm going to use this reference triangle and express the trig function of that angle, u. This is the reason why I wanted to go from an answer in terms of 2u to an answer in terms of just u, because my original substitution only involved u, and it leads ultimately to this reference triangle, which is helpful for doing trig functions of u. It is not helpful for doing trig functions of 2u. The next step of the back substitution is going to look like the following. 8 times u, and u is the arc sine of x over 4, plus 8 times the sine of u. So actually the sine of u is already converted to x's by this statement alone, so x over 4 will be the sine of u. So I've done that part. Now I'm going to do the cosine of u next, and here it's helpful to use this reference triangle to get the cosine of u. Cosine is adjacent over hypotenuse, so it's going to be the radical 16 minus x squared, which is the adjacent over 4, and that will be the value of cosine of u. Radical 16 minus x squared over 4. And then we have the plus c at the end. So all of this here, these were the tools for doing our back substitution, so that I could ultimately go from this step to this step. And then of course there's a little bit of simplifying we could do over here. We have 8 arc sine of x fourths plus, here that's 4 times 4 is 16, but there's an 8 up there, so this is going to wind up being 8 over 16, which is a 1/2, x times the square root of 16 minus x squared, and then plus c. And this is a good place to stop. I do challenge you to take the derivative of this answer and see if in fact it does in the end simplify to this expression. I recommend you do that. It's good practice with the differentiation, and it builds confidence that you do in fact have a valid antiderivative. So this is a pretty interesting thing that happened here. Trigonometry became a very useful tool in accomplishing an antiderivative for a problem that didn't feel like it was any way connected to trigonometry. At least it didn't feel that way. Okay, now I'm going to go backwards here and discuss what this table is talking about. This kind of substitution, known as a trig substitution, that makes use of the Pythagorean identity, right? That Pythagorean identity was this step right here. And this was a very important step because it allowed me ultimately to simplify the radical to get to a point where there was no radical. There's going to be 3 different scenarios where you're going to want to do some kind of trig substitution so that you can make use of the Pythagorean identity. The one we just illustrated was this case. We had a situation where I had some number, which we're calling a squared, that was the 16, minus some function being squared. In this case, it was very simple. It was a 16 minus x squared. Notice what I let x equal. I let it equal 4 times the sine of u. This is the substitution that you want to do. You want to let the function equal a sine u, where a is the square root of whatever number is right there. And whatever function is sitting right here, in our case here, that function was simply x, right? It was x that was being squared. So that's what you want to put right here, is let x equal a sine u. So as another example to illustrate this, this problem right here. So if I have 5 minus and then x minus 2 squared, and I want to do a trig substitution on this, I would identify what the function is that's being squared. That's x minus 2. So I would say, okay, let x minus 2 equal. Then I want it to involve a sign, and then with an a in front, where a is the square root of whatever number is in front of the subtraction. In this case, that's a 5. So think of that 5 as the a squared. Therefore, the a would be its square root. So I need a radical 5 in front of this sine u. Okay, this is what you would do as a substitution. Now I'm going to actually do this substitution, right? I'm going to change this x minus 2 into this radical 5 sine u to show you how the Pythagorean theorem gets used. So we wind up getting 5 minus, but instead of x minus 2, I'm having a radical 5 sine u, and that's being squared. Well, this just winds up being 5 minus, and when you square the radical 5, you get back to 5, and then you square the sine, you get sine squared. We want these two numbers to be the same ultimately, so that it can be factored out. And that leaves now a clean 1 minus sine squared, which we can convert to cosine squared using the Pythagorean identity. Now let me show you the other two types. I call this the difference of squares type 1, where you have a number minus a function squared. That's when you use a sign in your trig substitution. Now let's go over to this case over here, a sum of squares. If you have a sum of squares, something of the form a number plus a function squared, then you want to use this trig substitution. Let's illustrate it with this 9 plus x squared. The f of x in this role is just whatever's being squared. So in this case, that's just x. We're going to let x alone be equal to, the a here is going to be the square root of that 9. So we need to put a 3 there, and then a tangent u. It's the fact that this is a sum of squares that dictates the use of tangent. And let's see what happens when I do this substitution. Replace this x with 3 tangent u. And we get 9 plus 3 tangent u, and that's being squared. Well, when you square the 3 to make it a 9, and you square the tangent, now you can factor that common 9 out, and you're left with 1 plus tangent squared. And the Pythagorean theorem for 1 plus tangent squared converts it to secant squared. And then the last case, if you have this type, I call it type 2 difference of squares, function squared minus constant, then you want to use a secant substitution. See how that works. All right, so this one will be a little bit tricky because we have a coefficient in front of the x squared here. What function is being squared here to lead to 4x squared? In other words, if you were to change this to something squared minus 1, what would be that something? So you should just have a 2x sitting right there. So you do see something being squared, minus a constant. All right, so functions being squared, which is 2x, we set equal to a secant u, where a is the square root of this constant. So in this case, just a 1, then secant u. So this is the substitution I would want to make here so that I could make use of the Pythagorean theorem down the road. So change 2x to secant u, and that's just being squared, and minus 1. And the Pythagorean theorem says secant squared minus 1 is the same thing as tangent squared. Okay, there are 3 illustrations of the 3 different scenarios in which you might want to consider doing a trig substitution, and the type dictates which trig function should be involved in your trig substitution. Okay, let's do this next one here. Square root of 16 minus x squared. Oh, so that's the same type as the one we just did, except this time it's a definite integral. So I'm just going to make sure that we know how to go through the motions of doing a definite integral when a trig substitution is required. So one way to do this is to ignore the limits of integration and essentially repeat everything that you see in this picture here. In other words, I'm just going to do a little bit of copying and pasting, and we can just put an evaluation bar now and say evaluate from 0 to 4. Okay, we'll plug 4 in first. We get 8 arc sine of 1 plus, now this would be interesting when you plug in the 4 right here, you're going to wind up getting 1/2 times 4 times 0. And this is what you get when you plug 4 in. Then you go minus, and then you plug in the 0. We're going to get an 8 arc sine of 0 plus, and then when you plug 0 into this part of the antiderivative, right there specifically, that's going to 0 everything out as well. So our answer is 8 arc sine 1 minus 8 arc sine 0. So when you're doing an arc sine of 1, you are trying to find an angle between negative 90 degrees and positive 90 degrees where the sine is 1. I recommend you find a unit circle that you can reference. The only point on the unit circle that has a y-coordinate 1 is at the top of the circle, and that corresponds to the angle of pi halves. Pi halves is the angle at which the sine is 1. Therefore, the arc sine of 1 is pi halves. And the arc sine of 0, what's the angle at which the sine is 0? Well, that angle is 0. And then 8 times pi halves is going to be just 4 pi. The next thing I want to do is connect this to a meaning, right? So we're doing a definite integral of a function, 16 minus x squared. Let's go to Desmos to do this. And I'm going to just graph y equals the square root of 16 minus x squared. From the image, it looks like we got the top half of a circle of radius 4. By way of review, you'll recall that if you have x minus h squared plus y minus k squared equals r squared, this is the general equation of a circle that's centered at the point hk and whose radius is r. So specifically, if the h and k are zeros, then your general formula looks more simple. And this is a circle centered at the origin, and the radius would be r, so this would be the point r comma 0. And if you take this equation, which makes the entire circle, x squared plus y squared equals 16, we'll say, it gives you the entire circle centered at the origin, radius 4. Whereas this equation here just gives you the top half. So they aren't functions of x in the sense that they fail the vertical line test. But if you were to take this expression and solve it for y, so subtract the x squared, you get y squared is equal to r squared minus x squared, and then square root both sides, you get two possible answers, plus or minus the square root of r squared minus x squared. This is how you turn the circle into two different functions. The plus of these radicals gives you the top half, and the minus of these two options gives you the bottom half. Right, so if you're going back over here and you want the bottom half, then just put a minus sign in front of this, and you've got the bottom half of the circle. So separately, bottom half and the top half are functions of x. They pass the vertical line test. Now we're integrating from 0 to 4. So you're integrating this from 0 to 4, then you're really finding the area underneath this curve but above the x-axis. So this definite integral represents the area effectively of a quarter of a circle of radius 4. So if you got a circle and we want a quarter of it and the radius is 4, then we know that the area that's shaded there is 1/4 of pi r squared. And if the radius is 4, then we're going to have 1/4 of 16 pi, which is just 4 pi, confirming what we got using an antiderivative and plugging in values. Okay, and then finally, what if you were just doing this from the very start? Let me show you a different way that involves a change of limits when you do the change of variable. We have the integral of square root of 16 minus x squared dx. It was integrated from 0 to 4. By default, these numbers are specific values of the variable indicated by the differential. In other words, they're x coordinates. When I make the substitution that I want x to be equal to 4 sine u, therefore the dx will be 4 cosine u du. Typically, when you do a change of variable on a definite integral, then you want to also change the limits of integration. And the way we do that is, okay, well, make a table of points. You know, if x is 0, then what's u? And if x is 4, then what's u? Plug 0 in for x and solve this for u. So divide by the 4. So 0 is equal to the sine of u. And we're trying to find an angle where the sine is 0, and that angle is also 0. Right? Sine of 0 is 0. Now plug in 4 for x. So we have 4 equals 4 sine u. And divide by the 4, we get this statement. Now we're trying to find an angle where the sine is 1, and that angle is pi halves. When I make the change to the new variable, I could also change the limits. The square root of 16 minus 16 cosine squared. I'm skipping some steps. At this point here, you're going to just see repetitions of all the steps that we had to do up here in the first place, right? And so skipping those steps, it boiled down to the following integral, and I'm going to evaluate between 0 and pi halves. Now, I don't need to do the back substitution when I do it this way, because I converted the limits to u coordinates. So once I have an antiderivative in terms of u, I can just plug in these numbers for the u's. I don't need to try to do the back substitution. So in other words, this whole side of this, I don't need to repeat. Right? I pretty much stopped as soon as I got here, and I'm plugging in u coordinates. And when we do that, what do we get? 8 times, plug in pi halves for u, so pi halves plus 1/2 of the sine, and then double pi halves is pi, so sine of pi, minus 8 times, and then plug in 0 for all the u's, 1/2 of the sine of double 0 is 0. The sine of pi is 0, and sine of 0 is 0, so those all zero out. This whole area over here zeroes out entirely, giving us just 8 times pi halves, and that gives us the 4 pi as well. Okay, let's do another example. We've seen now really only this type 1. Let's go to this type next, something of this form. Okay, I see a sum of squares, and I don't necessarily see a regular basic substitution as being useful, because if I let u equal the denominator, I'm going to need a 2x to create my du, and there's no x up here. So if you don't see a regular substitution as being useful, but you see a sum of squares, think type 1 trig substitution. So I'm going to let the function that's being squared is just x, and then we take the square root of that number and x, which is 3, and when it's a sum of squares, I want tangent to be the substitution. All right, so dx will be equal to 3 secant squared of u. So this becomes a new integral of 1 over 9 plus 3 tangent u, that's being squared, and then times the dx, and the dx has to be changed to 3 secant squared of u du. And we'll see what happens here. That's the same thing as 9 tangent squared. So we get an integral of 3 secant squared of u over 9 plus 9 tangent squared of u, and then du. Okay, from here, we can factor out the 9. That leaves 1 plus tangent squared. And then I'm going to use Pythagorean identity on 1 plus tangent squared. That's the same thing as secant squared. And 3 over 9 is the same thing as a third. So this is actually going to simplify very nicely for us. It's going to get to the point where all the trig cancels, which gives me 1/3 of u as the antiderivative. Make sure you don't say 1/3 of x plus c. And now all we have to do is a back substitution. Notice there's no trig of u. There's no sine of u, tangent of u. So I'm not going to bother doing a reference triangle. I'm just going to take that expression and solve it for u. Divide x by 3, and then to get u isolated, we need an arctangent. So u will be the arctangent of x thirds. So over here, we just got to change this u to that expression, and we're done with this one. And there it is. Here's a problem that I want to work on. I do notice that a regular substitution will work here. Notice that x squared minus 4, if you let that equal to u, then du will be 2x dx, and there's an x there, so I could put the 2 there and put a 1/2 in front and then construct the du and finish this problem very easily. You know, this doesn't always happen that you can also do a u substitution, but I just want to use this to illustrate that I'm going to do a secant substitution and get an answer that's the same answer I would have gotten if I'd done a regular substitution. And so I notice there's a difference of squares here, and it's of type 2, meaning it's a function squared minus a constant. So then the function that's being squared is x, so that's what I want to let equal to, and then I take the square root of that constant, which is 2, and then do a secant. Okay, so then the dx will be 2 times, and derivative secant is secant tangent, and then du. So after I make those two changes, everything that's an x, and there's x here and here, needs to be turned into 2 secant u, and then this dx needs to be turned into this 2 secant tangent du. So this will become an integral of, focus on that x, change it to 2 secant u, times the square root of, I'm going to change this x to 2 secant u, but then also do the squaring of it. So when I square 2 secant u, I get 4 secant squared u, and then we have the minus 4 next, and then we have the dx, which gets replaced with 2 secant u tangent u. All right, so the magic's going to happen right here when we get to use the Pythagorean theorem. I'm going to factor the 4 out, and then the Pythagorean theorem will change that secant squared minus 1 into tangent squared. And now I can square root the 4 and the tangent squared separately, another 2 and a tangent of u. Now combine all the constants. I'm seeing 2 times 2 times 2, that's going to give me an 8. I can pull that 8 out to the front. I'm seeing a secant times a secant and a tangent times a tangent, so a secant squared of u times a tangent squared of u du. All right, so the question is, how do we integrate this? Well, a regular substitution will work here because the derivative of just tangent is secant squared. So if I can't use u's already been taken, but a new variable, let's go with v. If I let v equal tangent u, then the derivative of v is present, so I can construct the dv. So we can just do a basic substitution here. Let v equal tangent u. dv will be secant squared of u du. And so this integral will become 8 times v squared dv. The dv came from the secant squared times the du, and then that tangent squared is just v squared. Now I can anti-differentiate with respect to v. Divide by 3, new power becomes 3. Now do a back substitution. Change the v back to tangent, so we have tangent cubed of u. And then we have to do a second back substitution back to x. So we're going to need a reference triangle. I'm going to grab this line right there. I'm going to use this statement to create a reference triangle. I'm going to divide by 2, so x halves is equal to secant of u. I'm going to make my reference triangle. I'm going to call the angle u. The secant of u is hypotenuse over adjacent. The other side now will be the square of the hypotenuse, which is x squared, minus the square of the other leg, so minus 4. So the tangent of this angle is opposite over adjacent. So we have 8/3 times the tangent of u, radical x squared minus 4 over 2. And that needs to be cubed still, and then plus c. Right, you cube the top and you cube the bottom. If you cube the denominator, it gives you an 8, and that cancels with the other 8, giving you just a 1/3 is the constant. And then you could change this radical x squared minus 4 into x squared minus 4 to the 1/2 power, and then when that gets cubed, the powers multiply. So you could say something like this, x squared minus 4 to the 3/2 power. And this is a good place to stop. Keep in mind that this process was a little bit longer than it had to be, because if you had done a regular substitution on this to begin with, just let u equal x squared minus 4, it would have taken you to this answer rather quickly. The purpose of doing this example wasn't to show you the most efficient way to do this problem, it was simply to illustrate how a secant substitution can be helpful. All right, this problem is a little bit involved because it's the case where you have a prime quadratic denominator. So quadratic means you have something of the form, right, ax squared plus bx plus c, which is the form you see down here. Prime means that you can't factor it. We're going to do what's called completing the square on this denominator. Now to complete the square, let's say you had an expression like x minus 3 and you wanted to square that. When you FOIL this, you get x squared minus 3x, so minus 6x, and then plus 9. And this is called a perfect square because it factors into 2 identical factors. Let's say you didn't know that third number though, and you had to determine what number to put right there so that you had a perfect square. Well, you recognize that the minus 6x came from a combination of 2 identical terms, minus 3x and minus 3x. So take minus 6 and cut that in half to get minus 3, and then square that to get this missing number 9. And that's how you can determine what number needs to be there so that you can go backwards and factor this into 2 equal things. By the way, if that was plus, then this would be plus 2. So I'm going to take these first 2 terms of this prime quadratic denominator and complete the square. Right? Determine what number needs to be right here so that we have a perfect square. You take the coefficient of the x, which is 2, you cut it in half, and then you square the result. And that tells you what number needs to go right there. Right? So to be more general, if that was a b, then what would be different here in the process? That would be a b. So in this case here, we've determined that it needs to be a 1, but currently I have a minus 2. Well, this isn't a problem. I simply put the number I want to be in there and then also remove it right away. So this integral is going to look like x minus 3. We have x squared plus 2x. Put the plus 1 there, but counter it immediately with a minus 1. Because that's like we just added 0 to this problem. But then don't forget we need that minus 2 that's still there. And then you just regroup this. You focus on these 3 only, an integral of x minus 3 in the top. How this factors, it factors into x plus 1 quantity squared. And then those numbers there become a minus 3. And just like that, we've put this into a form where a trig substitution is going to be useful. Notice that I have a difference of squares here. It's a function squared minus a constant. That's the type 2 difference of squares that involves using a secant. So I'm going to do x plus 1 is my function that's being squared. It's equal to, take the square root of that 3, so radical 3, and then secant of u. This is the substitution I want to do, which means I need to determine what the dx is. So differentiate both sides. The derivative of x is 1, and the derivative of 1 is 0. So we get a 1 on this side, but then times dx is equal to, and the derivative of the other side is radical 3 secant u tangent u du. So I also need to find how to replace this x. So solve this one for x. X is equal to radical 3 secant u, and then minus 1. So now I have the means to substitute for that x plus 1, and substitute for that dx, right? All 3 of those things have to change. Okay, so what does this become? Well, the x that's up top here becomes this. So we get an integral of radical 3 secant u minus a 1. So there's the x, and then minus a 3. So I'm going to go ahead and just combine that right now and just say it's minus 4. So there's my new numerator. Denominator. I'm going to plug this radical 3 secant u into that x plus 1 and then square it. So I'm going to do the squaring as well in the same step. And when you square it, you get 3 secant squared. And then we have a minus 3. And then the dx became radical 3 secant u tangent u du. So this is looking really messy right now, but it's going to simplify into something that we can actually integrate. And the key is the fact that we're going to be able to use Pythagorean identity down here on this part. So we can factor the 3 out. Let me put this numerator in parentheses. This radical 3 I'm going to factor out, and these 3's I'm going to factor out. So that gives me a radical 3 over a 3 in front of this integral. Radical 3 secant u minus 4 inside some parentheses over a secant squared minus 1. That radical 3 I factored out, but I still have those, the secant and tangent. Here's Pythagorean theorem's going to kick in right there. That's going to become a tangent squared. Now I can look for some simplifying. We have this tangent is going to cancel with one of those tangents. And here I'm going to distribute the secant and split the tangent up under each part. And think of this as two separate integrals and see if we can't figure out how to integrate these. So we have a radical 3 secant squared of u over a tangent u minus a 4 secant u over tangent u. Okay, so we may have to approach both of these as two different methods. In this case here, notice that there's a tangent present and a secant squared present. That's a good clue for doing just a regular substitution. If I let w or v or some other new letter, I can't use u because u has already been taken, but let w equal the tangent of u, therefore the dw will be secant squared of u du. And over here, I'm just going to convert these to sines and cosines. Watch what happens here. You have a secant cubed, which is 1 over cosine u, over a tangent, which is a sine over cosine. When you invert and multiply, you get a 1 over sine, which is the same thing as cosecant. Right, so just converting that to sines and cosines turns it ultimately into just a cosecant. We have radical 3 over 3 in front. The first integral is going to wind up being, let me put some brackets around all this, because this radical 3 over 3 is going to affect both integrals. The first integral winds up being just a radical 3 over w dw. And the next one is going to be an integral of 4 times the cosecant of u du. So only the first one that I changed to w's, I kept this one in terms of u's. So using two different methods for the two integrals. Okay, so that gives me radical 3 over 3 as our coefficient here. The first antiderivative is radical 3 natural log of absolute w minus 4 times, and then the antiderivative of cosecant was natural log. Remember, you have two options here. Let's go with the cosecant of u minus cotangent of u inside that natural log. Or you can do where the antiderivative involves a plus here, but you get a negative, so that would be plus plus. Right? So you could have done both those plus or both those minus, and it would be acceptable. Let's just leave it with both of them plus. Then you got the plus c. Now we've got some back substitutions to do here. We have several layers of back substitution. The first thing I have to take care of is that w right there. We've got to get that back into terms of u first. Right, what was w equal to? W is tangent u, so we've got to make that change. Okay, so now everything is in terms of u. I see there's a tangent u, a cosecant u, and a cotangent u. All these different trig functions of u that need to be back substituted. We're going to come right back up to right here and make a reference triangle. I'm going to begin by dividing by the radical 3. So we have x plus 1 over radical 3 is equal to secant u. And then right triangle, angle is u. And I want to label the hypotenuse over the adjacent. So the hypotenuse is x plus 1 and the adjacent is radical 3. And the other leg is going to be the square root of the hypotenuse that's squared. So we have an x plus 1 squared minus the other leg squared. Well, radical 3 squared is just 3. And now I can do the back substitutions. I can use this as a reference triangle to do these 3 underlined trig expressions involving the angle u. Also, what I'm going to do is distribute this radical 3 over 3 to both these coefficients. So let's do both of those things at the same time. So radical 3 times radical 3 is just 3 over 3 makes a 1, so that's nice. We get just a natural log of the tangent of u, and looking over here, the tangent is opposite divided by adjacent. There's the opposite divided by the adjacent. Plus, now distribute this radical 3 over 3 to that 4. So we have 4 radical 3 over 3 as this coefficient, another natural log, absolute, and then cosecant of u. Well, looking at our reference triangle, cosecant of u is our hypotenuse divided by the opposite. So we're going to get x plus 1 over the opposite, which is that radical function, and that does the cosecant of u. And then we have to do plus cotangent of u. Cotangent is the adjacent divided by the opposite. So the adjacent is radical 3, and divide that by the opposite. Whew, and we are done.